So the goal of this is just to look at another example from Module 6, which was our first time looking at quantitative data. So for our example, we're looking at delays at Chicago O'Hare Airport and trying to see how long they are. So we took a random sample of 87 delayed flights at that airport, and we recorded many pieces of information, but one of them was the length of the delay, which is measured in minutes. So who is our population? So here we have an example that does not actually involve people as our population. What we are looking at here is all delayed flights at this airport. So technically the Chicago O'Hare Airport. So our variables, what information are we getting from them? Well, we're going to get the length of the delay. So the delay's length, which is measured in minutes. So this is going to be a quantitative variable. Next, we're going to look at the histogram and summary statistics to interpret some things from it. So we're given the mean, the median, our min and max, also given our sample size, and then we'll need the standard deviation when we start talking about empirical rule versus Chebyshev's rule. So here, how would I write this? So I'm going to say when looking at delay lengths of the delayed flights at this airport, so the Chicago O'Hare Airport, the distribution here is what would our shape be here. So if I look at this one is definitely not normally distributed. It's not symmetric at all. So which way is it skewed? So I like to pretend that this is a slide. So if I think about what my slide would look like here, which way would I slide? So if I start at the top, I'm going to slide right, which means it's going to be skewed right. And are there any unusual numbers here? There definitely is this one out here that had a very long delay length of 448 minutes. So we definitely have an unusual observation here of the 448 minutes. Our mean, or the average delay length, is 64.31 minutes. And the median, so 50% of our delayed flights had a delay length less than our 47 minutes. The smallest delay length was 16 minutes, while the largest was our outlier, so our 448 minutes. Now let's talk more about using this standard deviation by discussing Chebyshev's versus the empirical rule. So which one should I use here? Well, I know the empirical rule should only be used when I have a normal distribution. So I look back at my picture here of my histogram. There is no way this looks normally distributed to me. So I'm going to have to use Chebyshev's rule because my data is skewed right. So now we're going to use that rule to create and interpret an interval that is 2 standard deviations from the mean. So our mean, going back to our numbers here, was 64.31. And our standard deviation that we're going to use is the 58.08. So doing our math there, let's see what numbers we get. So let's first talk then about this number I got here on the bottom. So we're looking at the length of a delay. You can't have a delayed flight that has a negative number of minutes of a delay because that would actually mean that the flight took off early. So the smallest number this could technically be would be 0. So then as I'm interpreting this, so for Chebyshev's rule, we know that 75% or more of the delayed flights at Chicago's O'Hare Airport are, now a lot of times we say between here, but since the smallest delay length could be a 0, I don't really need to say between 0. So it's going to be less than 180.47 minutes in delay length. Now we're going to move on to the sampling distribution side of Module 6. So in 2010, they reported a mean delay length of 75 minutes and a standard deviation of 48 minutes. We're going to use that information and knowing that we sampled 87 days to find our sampling distribution. So we were given a mean of 48 minutes. We were given a standard deviation of 40. Oops, sorry, I got my numbers confused. So our mean was the 75. I apologize. The standard deviation was the 48. And then we sampled 87 days. So first, if I check my conditions here, I don't really have any bias in my sample here. And then we either need to know the population was normal. We know that's not the case because our graph looked nowhere near normal. Or we needed to have a sample of at least 30. That we do because we have 87 flights that we sampled. So our conditions are met. So then we can say that y bar will be approximately distributed normally. Remember, the mean of y bar is just mu, so that's going to be our 75. The standard deviation of y bar is sigma over the square root of n, so that will be 48 over the square root of 87, which gives us approximately 5.146. So then these numbers are going to be what we plug in for the mean and standard deviation of y bar. Now we're going to use that sampling distribution next to calculate a probability. So from our 87 days, we found a mean of 64.31 minutes. We're going to use our sampling distribution to find the probability of observing a sample mean that was less than this if nothing had changed. So I'm going to start by drawing my picture here. So we're going to be centered at that population mean of 75. And then when I draw my picture, I go up to 3 standard deviations away. My standard deviation that I'm using here is this 5.146 because we're trying to find the probability of a mean. So I've got to make sure I'm using then the standard deviation of the mean. So our standard deviation here was the 5.146. So that's going to be my size of each of these pieces. And then just doing my math here. So here are my numbers along the bottom. And then our sample mean was 64.31, which is roughly about here. And then I need to figure out which way I would shade. So it has the less than, so we're going to shade to the left. So then next we're going to find our z, which if I look at my formula sheet, looks like this. So our sample mean was that number we just put on the picture. That's 64.31. The mean of the population was 75. And that whole number on the bottom we've already calculated here is that 5.146. And so what I get is negative 2.08, which should make sense because we're 1 to a little bit more than 2 standard deviations below the mean. Since we're shaded left, we can go straight to the table to get our probability. So just using our z table, we should find 0.0188 for our probability. So if I'm going to interpret this, so assuming the mean really is 75, or the average delay length at the Chicago O'Hare Airport really is 75 minutes, the probability of getting a sample mean that is less than our 64.31 minutes with our 87 flights is, and then our probability was 0.0188, or what would be 1.88%. So that completes the extra example here for Module 6.